Imagine if the very foundation of how large language models learn wasn't just, predicting the next word. What if it was about reasoning through it? Like truly reasoning, deeply, verifiably. Could we actually build that deeper intelligence right into these huge AI brains from the get-go? Today, we're taking a deep dive into reinforcement pre-training, or RPT. It's really groundbreaking new idea from researchers at Microsoft Research, Peking University, and Tsinghua University. Our mission here is to unpack how RPT could fundamentally redefine language model pre-training, how it might make them smarter, more robust, and maybe even incredibly scalable. Okay, so for those needing the quick version for, say, a short form edit, here are the key takeaways. RPT fundamentally changes LLM training. It reframes that standard next token prediction task we all know into a reasoning task using reinforcement learning, RL. And what's really cool, what's innovative, is it uses verifiable rewards. But get this, they're derived directly from massive amounts of unannotated text data. This lets RL scale up for general pre-training in a way we just haven't really seen before. The result, well, models that aren't just better at predicting the next token, accuracy-wise, but they seem to develop a deeper, more generalized understanding. And it helps minimize problems like reward hacking.
Right.
Think of it like building a much stronger foundation, maybe adding a layer of reasoning underneath existing methods, really boosting the core capabilities.
So, hey, let's drill down a bit now for our technical audience. We know LLMs are amazing, right? Largely thanks to scaling up that next token prediction objective on huge data sets. It's been the workhorse.
It really has.
But, for all its power, it does feel like maybe we're missing something. That piece about true verifiable reasoning. What's been the main roadblock there? Getting LLMs to actually think, not just infer statistics.
That's precisely the challenge this research tackles head on. You're right, self-supervised next token prediction, incredibly effective, super general purpose. But when you try to apply reinforcement learning, well, current methods hit some real walls, especially around scale and generality. Take RLHF, reinforcement learning from human feedback. Powerful stuff for aligning models, sure. So very popular.
But it's expensive, right? You need all that human preference data. And maybe more subtly, those learned reward models. They can sometimes be gamed, reward hacking. That limits true scalability.
Okay.
Then there's RLVR, reinforcement learning with verifiable rewards that uses objective rule-based rewards, which is great for avoiding reward hacking.
Seems better.
Yeah, but the catch is usually the scarcity of the right kind of annotated data, like question-answer pairs or specific task data. So RLVR has mostly been stuck in domain-specific fine-tuning, not broad general-purpose pre-training.
Right. So if I'm getting this, we needed a way to kind of merge the best parts, like the massive scale you get from unannotated text, but with the reasoning power and robustness of verifiable RL, and crucially, without needing costly new labels.
Precisely. RPT aims to be that novel paradigm. It's designed to bridge that exact gap, scalable, self-supervised learning meets powerful RL.
Okay, let's unpack the mechanics then. How does RPT actually pull this off? How does it make that transformation happen?
So RPT reframes the whole thing. It's not just predicting the next token anymore. It's framed as a next token reasoning process. For any given context in the training data, the model is actually incentivized to, reason about what token should come next before it actually predicts it.
Reason before predicting. Okay.
And here's the clever part. It gets an intrinsic verifiable reward based on whether its final prediction matches the actual ground truth next token from the corpus itself. This is really key. It turns all that readily available, unannotated text, the stuff we already use for standard pre-training, into a huge data set for general purpose RL. No new annotations needed, no domain-specific reward functions to engineer.
Wow. Okay, so it's almost like teaching the model to pause, think it through, show its work internally, and then speak. And it gets rewarded for the correct final answer, which implies the thinking was good.
That's a great analogy. And designing that reward function, that prefix matching reward we'll get to, was definitely a core part of the work. But before we dive into that, let's just quickly tick off the advantages this approach brings, especially for folks building these models. First, it's inherently scalable and general purpose. Like we said, it reuses existing data just in a smarter way for RL.
Right, no extra data cost.
Second, reward hacking is much less of a concern. Because the reward is so direct, did you predict the actual next token correctly after reasoning?
It's rule-based.
There isn't a complex learned reward model for the agent to exploit. It's very straightforward.
Much cleaner signal.
Exactly. Third, by explicitly pushing these next token reasoning patterns, RPT encourages deeper understanding. It's not just memorizing sequences. The model learns to explore hypotheses, like why a token should follow. That should lead to more robust, generalizable representations. And finally, this internal reasoning process during pre-training. It effectively lets the model spend more computational effort, more thought on each prediction step during training. You can almost think of it like applying inference time compute scaling, but doing it token by token during the training phase itself.
Interesting.
And this directly translates to better next token prediction accuracy. The results bear that out.
That makes a lot of sense. But I mean, there's always this nagging question, isn't there? Even with rule-based rewards, could the model just get really good at mimicking reasoning without truly understanding? Like, the clever student who aces the test but doesn't grasp the concepts.
It's a valid point, and something researchers are always mindful of. But with RPT, the reward is so tightly coupled to the ground truth from this massive, diverse corpus. It becomes really hard for the model to consistently get the right answer just by faking it. To predict accurately across so many contexts, especially the challenging ones RPT focuses on, the model is almost forced to develop more robust, generalizable reasoning patterns. It's not rewarded for showing reasoning per se, but for getting the right token after a reasoning step. The prediction accuracy itself becomes the verifiable outcome of that internal process.
Okay, I see the distinction. Now let's make this really concrete for practitioners listening. Can you paint a clearer picture? What does this next token reasoning look like inside the model compared to standard prediction?
Absolutely. Let's take that example. The text says electric force grows with charge. What comes next?
Okay.
Standard next token prediction. The model crunches probabilities based on the context and directly outputs, say, size. It's a straight statistical inference, p-size context. With RPT's next token reasoning, the model first generates an internal kind of thought process. It might internally generate something like, okay, context is physics laws, grows with charge, likely talking about Coulomb's law. What's the other variable? Distance. It decreases with distance squared. So the concept related to how it changes with distance, maybe size isn't quite right. Or wait, maybe it means magnitude. Let's consider alternatives. Magnitude, strength. Looking at the sentence structure, maybe it just wants a simple property. Okay, considering the prior phrase structure, maybe it is going for a simpler concept. Let's hypothesize box size for now, and then it outputs size.
Wow, so it's like the internal monologue with brainstorming, self-correction.
Exactly. Patterns like brainstorming, critiquing its own ideas, maybe considering alternative phrasings. That's the kind of internal process RPT encourages. And technically, how they achieve this is by training the LLM using on-policy reinforcement learning. So the model learns from the trajectories it generates itself using its current policy.
Okay, on policy. Got it.
For each context, it generates multiple thinking trajectories. The paper used, I think, G8. Each one includes that internal reasoning sequence and the final predicted token.
And that reward signal you mentioned. How does it verify correctness without labels, especially if the ground truth is just one word, like size? How does the prefix matching work?
Right, the prefix matching reward. This is pretty neat. The reward is 1 if the sequence the model predicts, which could be one token or multiple tokens, is an exact prefix of the ground truth completion sequence from the corpus, and its length matches a valid token boundary. Otherwise, the reward is 0.
Prefix matching.
Yeah, it's crucial because maybe the true next step involves multiple tokens. This allows the system to handle that. It can even potentially reward predicting parts of new or out of vocabulary words if they're tokenized that way. It makes the raw text itself the source of this verifiable rule-based reward signal without needing any external labels.
Okay, very clever. So the proof is in the pudding, as they say. Let's talk results. How well did RPT actually perform? Our listeners, AI researchers, ML engineers, they live and breathe empirical evidence.
Absolutely. And the results reported are quite compelling. They definitely seem to validate the core idea. So the setup. They used DeepSeek R1 DistillQuinn 14b as the base model. That's a 14 billion parameter model that already has some reasoning ability baked in.
Okay, a decent starting point.
And they trained it on OmniMath. That's a data set full of competition-level math problems and their solutions. So pretty challenging stuff that requires reasoning. But here's a really important detail. They did token-level data filtering. They didn't just train on everything equally. They prioritized training on the hard tokens.
Hard tokens, meaning?
Tokens with higher entropy.
Right.
Basically the ones that are harder to predict just from the preceding context, the ones where you'd likely need to reason to figure them out. This focuses the computational effort of RPT where it's most likely to develop that reasoning capability. Smarter training.
Makes sense. Focus the effort. So what did the language modeling results look like?
They found that RPT-14b got consistently higher next token prediction accuracy compared to the baseline model using standard prediction, and also compared to a baseline that used reasoning prompts but without the RL pre-training. And this held across easy, medium, and hard tokens.
Any specific numbers?
Yeah. For instance, on the easy tokens, RPT-14b hit about 45.1% accuracy, while the standard baseline was around 41.6%. So a noticeable jump even on the easier stuff, likely due to that internal reasoning overhead paying off.
Okay, better than its own baseline. But the thing that really jumped out at me in the paper, it wasn't just beating itself right, it was punching above its weight.
You're absolutely right. That was one of the most striking findings. The RPT-14b model actually matched the performance of a significantly larger model, the R1 Distill Q32b, on next token prediction accuracy.
A 14b matching a 32b.
Exactly. That strongly suggests RPT isn't just about adding parameters. It's highly effective at capturing complex reasoning signals and improving the core language modeling capability much more efficiently, getting more bang for your buck parameter-wise.
That's huge for efficiency. What about scaling? Does this RPT approach continue to improve with more compute?
Yes, it showed good scaling properties too. The next token prediction accuracy consistently improved as they increased training compute. And critically, it followed a clear power law relationship across all the data difficulties.
The familiar power law.
Right, which indicates it's likely a sustainable approach. You can expect predictable improvements as you invest more compute in RPT training. It's not hitting a weird plateau.
And what about downstream tasks? Does this better pre-training foundation help later on?
Seems so. They found that RPT provides a stronger starting point for subsequent reinforcement fine-tuning. Models fine-tuned on top of RPT reached better final task performance, and interestingly, they noted that models which just continued standard next token prediction training actually saw their reasoning abilities decline over time.
Really? They got worse at reasoning?
Apparently so, which kind of underscores that the RPT objective itself is crucial for fostering and maintaining that reasoning muscle.
Okay, what about general tasks? Did this math-focused pre-training generalize?
Yes, they tested a zero-shot on general benchmarks like MMLU Pro and Super GPQA. The RPT-14b consistently outperformed the standard R1 Distill Q114b baseline, even when that baseline used reasoning prompts. But even more impressively, it significantly surpassed the much larger R1 Distill Q132b model when the 32b was evaluated using standard prediction on these general tasks. Like a huge jump of around 22 points on MMLU Pro and 7 points on Super GPQA.
Wow, okay, so let's just pause there. What does this really mean for someone developing or using LLMs? It sounds like RPT isn't just a small tweak. Getting the performance of a 32B model from a 14B model that has massive implications for deployment, cost, accessibility. It feels like this is changing the game, suggesting that how you train, focusing on reasoning, might be as important or maybe even more important than just scaling up parameters. It makes the models more capable right out of the gate.
I think that's a fair assessment. It shifts the focus. And beyond just the numbers, the researchers also dug into how the RPT models were thinking differently. They did this cool analysis where they statistically measured how often the model's internal reasoning steps used keywords associated with different reasoning patterns, words like breakdown, alternatively, probably, deduce.
Trying to peek inside the black box, what did they find? Did the RPT models actually show different thinking patterns?
They absolutely did. The RPT-14b model's internal reasoning process looked markedly different from just standard problem-solving approaches. It showed something like a 161.8% greater use of patterns they categorized as hypothesis generation, and a 26.2% greater use of deduction patterns.
Hypothesis and deduction.
Yeah.
More active reasoning.
Exactly. Whereas the standard approaches relied much more heavily on just simple breakdown patterns, like step-by-step decomposition. So RPT seems to elicit a qualitatively different, more inferential, more exploratory kind of internal process.
Can you maybe give us a flavor of that, like walk through what that deliberative process might look like for a specific token?
Sure. Let's stick with that calculating vector magnitude example. A standard model might just predict steps. An RPT model's internal trace might look more like this. Okay, the context is calculating vector magnitude. The last sentence was explaining the formula. Logically, the next part should probably be about applying it. What are ways to apply it? Could show examples, could outline steps, maybe discuss methods. Hypothesis 1, examples. Hypothesis 2, steps. Let's consider the structure. The document uses markdown headers. Is a new section starting? Probably. Okay, Steps fits better with a structured explanation. Also need to consider low-level stuff. Should there be a space before the word? Yes. Okay, deduction points towards steps as the most probable continuation following the explanation. It's this multifaceted thing, analyzing semantics, structure, generating options, evaluating them, even thinking about formatting, all to deduce that single next token.
That's fascinating. It's not just a lookup. It's an active construction process. It really changes how you think about what's happening during pre-training. This feels like a big shift, especially considering how much focus has been purely on scaling parameters. This algorithmic innovation seems incredibly powerful.
I agree. It suggests that innovating on the training objective itself can yield potentially huge returns, maybe even comparable to just throwing more parameters and data at the problem. It opens up avenues for creating more capable models more efficiently. Now, of course, this was an initial exploration. It focused mainly on that 14B model and the OmniMath dataset, so the big next steps are pretty clear.
Scaling up.
Exactly. Applying RPT to even larger models, hundreds of billions or trillions of parameters, and training on broader, more general web-scale text data, that's crucial to see if these benefits hold and amplify at massive scale. We also need to really pin down the scaling laws for RPT. Define those predictable relationships between compute, data, parameters, and performance specifically for this training method. That would guide future development.
Makes sense.
And there's also interesting work to be done integrating RPT with other ideas, like hybrid thinking. Imagine a model that could adaptively trigger this deeper RPT-style reasoning only when it encounters a particularly challenging or ambiguous part of the input, saving computation otherwise. Fine-grained adaptive reasoning.
That sounds very efficient.
Ultimately, RPT really does offer a very promising new direction. It's about rethinking the core pre-training objective, moving beyond simple prediction towards embedding reasoning capability right from the start.
So, wrapping up, what's the big takeaway for you from this work? For me, it's that fundamental shift. Changing how we train, incentivizing reasoning from the ground up, seems to unlock a deeper kind of intelligence and efficiency. It's moving from rote pattern matching to something more like active inference, making understanding emerge from the data more directly.
I think that captures it well. By getting models to genuinely think about what comes next, rather than just statistically predict it, we're building a foundation for AI systems that are not only more accurate, but also more robust, more scalable, and potentially more capable of tackling complex reasoning tasks.
Well, that was a really insightful deep dive into reinforcement pre-training. It certainly gets you thinking about the untapped potential in these models and how smart training methods can unlock it.
Indeed. It's exciting to see innovation focus not just on scale, but on the fundamental learning process itself. It could lead to genuinely more capable AI.
And for you, our listener, maybe think about how this shift towards reasoning-based pre-training might ripple outwards. Could we see future AI tools that don't just give answers, but can naturally show their reasoning? How might that impact fields that rely heavily on complex, high-stakes reasoning, like science, medicine, or engineering? Lots to consider. We hope you enjoyed this exploration. We'll be back soon with another deep dive into the cutting edge of AI and tech research.